Okay. All right. So we went over the first example, at the short span between points in the plane, and the strategy for this one and for the next two and for some of the problems at the back of the book is basically to turn your condition. So you're trying to find, the shortest path between points. So you write the expression for the path, and its variation is going to be 0 with respect to changes in the path. So you try to write an integral like this and try to set its try to make it stationary. So it's going to be 0 with respect to a variation, or at least to the first order in the deviations. Right. So we manage this for the shortest path by starting from some integral of this path distance, and then manipulating this to make it look like this one. It's just in this case, it's just one step. And so you just take into account parentheses of dx, and you end up with some expression here. But once you get the expression in this form, then the equations you're looking for, the solution that makes this the path that makes this stationary, is going to satisfy the earlier equations, or earlier Lagrange equations. So this is the general strategy. Now the second example in the book is which one? Minimum surface of revolution. Yeah. So I remember this problem very well because this was the problem that was asked me in my PhD qualified oral exam. So I was incredibly lucky in that exam. I actually looked at derivation of they asked me to write this Euler equation and then apply it to that problem. They didn't allow me to start from this, but I was very lucky. I actually looked at the derivation the night before, so I managed. It was crazy luck. So the surface of minimum revolution is that you have, say, 2 points. Okay. So x1, y1. So this is my x-axis, this is my y-axis, and x2, y2. And I'm going to have some curve between these two, and I'm going to revolve it around the y-axis, like so. So this is going to form a surface, and we want to have this to have the surface of a minimum area. Yeah, so the way this was asked me in the PhD qualifier exam was that somebody said, I have 2 rings of given radii, and I want to make a lamp out of these by putting some cloth over these, so the endpoints are going to be completely empty, and the height of the lamp is fixed. So this, of course, fixes the relative positions of these two, and it is asking for the minimum area for the surface of revolution. And so we need to write an expression. We need to write our J function. Let's call it section as the area. And how do we get this area? We are going to, of course, write some integral for this area. And how do we write this area? Well, one way to think about this is to think of the strips. So I take these little strips, and I add the area of these strips up. So if I take this, circular strip and open this up, what do I get? Well, the circumference is going to be just the x coordinate 2 pi, the x coordinate. So this is 2 pi x, and the thickness is going to be just ds. And ds, as you already know, is 1 plus y prime square root times dx. And I'm going to integrate this from one point to the other. So this integral is, so this one is going to become from x1 to x2, this thing over here, 2 pi x squared of 1 plus y prime squared dx. And voila, we have the desired form, right? This is our function f. In fact, we can take this of y prime x times dx. And so the path, the shape that's going to make this an extremum, the stationary value of this total integral, is going to be given by further Lagrange equations. So this is very similar to solving a problem with the Lagrangian. Writing the Lagrangian could be tricky, but once you write it, the rest just is very simple. By automatically putting your Lagrangian over here, you're going to get your equations of motion. So once you get this integral in terms of some function that looks like this, by plugging it in here, you're going to get your solution. There's no, you don't even need to think about it. But to write that, of course, you need to think. So what's the solution in this case? Del f del y is again 0. So this is kind of cyclic inlet coordinate. And del f del y prime is x y prime by 1 plus y prime square. And when you substitute this here, you see that the derivative of this with respect to x is a constant, is 0. So this thing must be a constant. Must be a constant. Okay. This is the same thing that happens again and again. That when you have this function for the mechanics case, when you have Lagrangian is independent of one of the coordinates, then the corresponding there's going to be something conserved corresponding to that coordinate. Right, and well, you go through this integration, so it is an integral and so on and so forth. The solution is going to be x equals a cosine hyperbolic y minus d over a. And this cosine hyperbolic, this curve is known as catenary. Do you know what a catenary is? Have you heard it before? Someone is speaking, but I can't hear you.
I said yes, hocam.
Okay, so what's catenary?
For example, if we have a spring or rope of say fixed size, and then if we fix the endpoints, it becomes the shape in the catenary shape, minimizing the potential energy of the full body.
So it's the chain curve.
Yes.
If you hang a chain, if it is a mass, then it's going to have this form. Looks like a parabola, it's not. It's different. Now, there's one thing peculiar here, that you can write this equation in this form. So x over a is going to be cosine hyperbolic of y over a minus b over a. So everything scales by a, which means that there's sort of some scaling freedom over here. And then if everything is scaled by a, you have a single parameter. You don't have two independent parameters, b and a, but just a ratio and phasor equation. So this means that in some cases you're going to have more than, so strictly speaking, this a and b will be determined by these values of x1, y1, x2, y2, right? So distance between these two, in fact, and their radii, the distance from the y-axis. But in some cases, you're not going to be able to find solutions. And in some cases, you're going to find two solutions. Okay? You're going to be able to draw two catenaries from these given points. This is the first remark, and it's because of the scaling property. This one, I mean, it's not surprising. Sometimes you can't find solutions that happen all the time. You get some equation, but there's nothing that passes through these given points. The second one is the solution. Now, this Euler-Lagrange equations apply under special circumstances. So I said that when I'm writing this function f, f plus alpha theta. Well, it's not necessarily y. I said that's arbitrary, but it's not. It's also logically differentiable. So if for some non-differentiable curves you get a shorter distance, this solution will not catch them. Okay? And in this case, it turns out there are some classes of solutions that this can happen. I'm not really sure when that does happen, but I think when they are far apart or when they are close to y-axis, obviously there are two scales in the problem, but there's this distance between them and their distance to the y-axis. I think when they are far apart from each other, there is a solution that kind of looks like this. Let me go to it. Call it. And something like that. Okay? And so you start from this point, you go to the y-axis, you come down, you come to the second point. This is these kinks at the end, and because of that, it's not twice differentiable, and because of that, it's not this solution is not caused by these cases. And there's a problem at the end of the book that asks you to experiment with the catenary solution and so on and so forth. I didn't try it myself, but I'm sure what they are saying that you'll find is correct. And this is something to keep in mind. Right? So if this corresponds to something physical, some mechanical system, you're not going to get solutions like this, obviously. But whatever problem you're solving, perhaps there's a solution where the actual solution is like this. And this was, when I first heard about this, it was very surprising to me. I heard this when I was an undergraduate, when I was first learning about calculus operations, because it looks to me like you could start with the solution and like make this differentiable by adding very small circular arcs over here, right? I mean, it's not differentiable at a single point. So you just take that point out, put a little arc, and you're not differentiable. So why does this not catch that solution? Okay? I have no idea. I actually still don't know the answer to this question. Okay? I know why it doesn't catch the solution, the kinks, because of the assumption on this, but I'm not sure what other what is preventing us not getting the solution. This little arcs over there, and perhaps I should look at the a problem at the end of the chapter and experiment a little bit, see if I can show that this kinky solution is actually a smaller area, and then if I add the arcs, it actually no longer is. I don't know. I can't imagine that will be the case because I can make this arc as small as I want, but maybe there's something there. If anybody learns the answer to this problem, please let me know. No, it's not something I've been continuously thinking about, but it's something in my mind for many, many years. So what? So it's probably 30 years, yeah. It's probably 29, 30 years that it's a problem that I don't know the answer to. And I never learned it because I wanted to figure it out myself, but at this point, it's obvious I'm not going to learn it myself. Any questions about this? Again, the strategy is the same. You write some integral that looks like this, and then you proceed to use Euler-Lagrange equations. And the hard part is generally writing the integral, coming up with that, if you know this already. Like, is this clear how I wrote the little areas? That dA is just this ds times 2 pi x, and that ds is, when you look at this figure, it's just a path. Does that make sense? Okay. I'll take the silence as something positive. Now, the third example is the Bragg-Stockholm problem. This is something very famous. It also has historical significance because this was solved by Bernoulli, and while solving this, he developed some principles of calculus of variations. It was also solved, I think, by Newton, who already knew calculus. But parallelly after solving this, he published his findings on calculus. And then Newton said, oh, I already know this, and so on and so forth. But you can read the story in Wikipedia, I'm sure. So, brachistochrone problem. Now, this problem is basically saying that we are given 2 points, and there's gravity. And what's the shortest path between these 2 points? So what kind of path will I follow under the influence of gravity that will allow me to go from this point to that point in the shortest possible amount of time? Now, it's not a straight line. Okay, so it turns out that you can, of course, put an inclined plane and go in a straight line, but that's not the shortest line. It turns out that it's a little bit better to, go on a steeper line first. So you gain some velocity because you're going down the gravitational field. You gain some kinetic energy, and then you go faster. Right? So this is somewhat similar to comparing this problem with this problem. Okay. So you have two inclined, two paths. One has a longer incline to begin with, and then goes on a longer incline at the end. This is starts with a shorter incline and goes up with a shorter incline. So let's go this one, two. First path is shorter than the second one. Right? It's obvious. This has some additional things at the end, but it turns out that if you go over the second one, you go faster. Not always, of course. I'm sure you can make this extreme like a triangle, and it's not going to work. But there are some videos on YouTube that you can check this out. That the straight path, when you're moving under influence of gravity, is not the shortest path because it's better to fall down in gravity, gain some speed, and this makes up for the increase in the length. So we're not looking for the shortest path, but the shortest time. So our integral is going to be something like this. That's what we are looking for, because it's short. So shortest path is, of course, a straight line. That's kind of tricky. Now, how do you take this and write it in terms of like a function that we know? So first of all, let's draw some coordinate system. I think traditionally it's drawn this way. Y is down, so it's going to be x1, y1, going to be x2, y2, and this dt is going to be ds by v. And I'm going to assume I start from 0 velocity. So it's actually better take this x-axis and move it over here. So I start at y equals 0, then I can write things a bit more simply. So I start at rest. Equals 0, and at y equals 0. Right. The second one costs nothing. That you can do without loss of generality. It's just shifting the origin of your coordinate system. The first one seems like a overzealous assumption, but again, you can show that it doesn't matter whether you start with some velocity or not. You get the same kind of curve. So how do I get v? So I want to write this in terms of x and y, and eventually get the function of y, the derivative of y with respect to x, perhaps, and then x. And I'm going to have something that's proportional to x. So I'm going to try to get an expression that looks like this. Oops. X dx, starting from this one. Now, ds I can manipulate. Okay, so ds is fine. ds is 1 plus y prime squared dx. So I'm half done. Yeah, I have my dx, I have some function of y prime. How will I write this v in terms of y prime, and x? I already told you, right? What do you do?
Conservation of mechanical energy.
Yeah, it's conservation of mechanical energy. Does everyone know what that means?
Yes, so the total of kinetic and potential energy will be same at both points.
Very good. So Mehlika Zeynep, are you with us?
Yes, hocam, I'm here. I'm listening.
Okay, so how do you use this? How do you use the sum of kinetic and potential energy same to get your V?
How do I use mechanical energy, or how do I get
Conservation
potential
of mechanical energy.
we take a derivative.
You take a derivative of what?
I take a derivative of what?
So I want to, write this dt. It looks something like this. So this dt is the path length divided by speed. Yes. So the path length is already, similar to this form. So I want to take the speed, and in the end, that ratio, path length divided by speed, is going to look like this. How do I write v in terms of the other stuff in my problem? Now, it has been suggested that we use conservation of mechanical energy, which I agree, which I already told you actually.
So the
How do you
initial.
use it?
So initially we have no
No,
kinetic
I'm not
energy,
asking
and
you. I'm not asking arbitrary person. I'm asking
okay.
Mehlika Zeynep.
I'm blanking out, but I know I can do it on paper. I don't know why I can't answer
Okay,
right now. I'm
that
so
happens to
sorry.
everyone. Don't worry about it. No, it's fine. Ali, do you know the answer? Ali, are you here? Okay. How about Ecem?
Hocam, is it about the potential being independent of time? We had a discussion on
Oh,
system
that's. I'm sure it's
conservative and-
related to that, but no, that's not what I'm after. Just I want an expression for V in terms of preferably y prime and x. So then this ratio is going to be in the form that I like. How can you write V in terms of y prime and x? So you're going here, you're here. Okay, so here you have some y prime and x. From this, how do you get V? Not
hocam,
necessarily as a function of all of these. In fact, it depends on only one.
so since we said that the energy is conserved, so the lost potential energy will turn eventually to the kinetic energy. So there we
How do you
can.
write this mathematically?
So the only potential energy is changing in the vertical direction. And then if we know the mass and the gravitational
You don't
acceleration.
need the mass. Mass cancels out.
Yes. So just g delta y is equal to the 1/2 v square, maybe.
Yes, and this h is in fact y. I started from
Yes.
y equals 0. That's why I want to make things convenient. Okay. Well, yeah. So now we have an expression for v. Which I can put down there. Now my integral then becomes so for ds I write this 1 plus y prime square divided by 2g y. I can take the square root of 2g out. Okay, it doesn't change anything. Times dx. So the function that I'm interested in is 1 plus y prime square by y to the square root. You can neglect the constants. That's not going to change anything. And I can use Euler-Lagrange equations to solve this. I think in the book they're not solving it. But they don't go, no, they don't take all the steps. but given this function, you can integrate it. And in fact, this is done in Torton and Marion. In the 5th edition, it's at page 211. So let me just sketch how you go about solving this equation. Let me fix this.
Hocam, sorry to
Yes.
interrupt, but Ulvi just texted me and asked me to let you know that he doesn't have a microphone.
Ah, okay, it's fine. Does he need to say anything else, or let me look in the chat?
No, I think he wrote something at the
Ah.
chat. I just wanted to
Okay.
get that over to you.
All right. So we have this, and we need to calculate, del F by del Y and del F by del Y prime, and then put into Euler branch equations. Right. So when you make that calculation, let me just copy from here. I don't want to do all these things. Wait.
Hocam, may I ask something?
Yeah, go ahead.
We are trying to find dt and ds over v we are looking for. So the particle is eventually falling down a little bit and gaining some velocity. But even though we represented ds in the form of our previous discussion, like we are looking for the minimal path, but maybe I thought like maybe we might be missing something like just assuming ds to be in the previous form. Is there something about it, or maybe I'm misunderstanding it?
So the form I'm using is this.
Like the Euclidean distance, you mean,
Yes.
right? Okay.
Yes.
So this doesn't don't makes hocam maybe Türkçe dönsem daha kolay edeceğim. Yani burada distance'ı Öklidyen bir şekilde ifade etmemiz, hani bu cismin en başta hızlanıyor olması bir sorun yaratmayacaktır, değil mi? Yani çizeceği path üzerinde. Yani yine de sonuçta x-y düzlemi de yani planar bir yönde hareket ettiği için.
Şimdi ben soruyu tamam bir kere first of all, is there anyone here who cannot follow Turkish? So if that's okay, I'll just respond in Turkish as well. Şimdi birincisi sorun yaratmayacaklarını ilk kastettiğinizi anlamıyorum. Bir etkisi olacak. Hani bunun hızlanıyor olması tabii ki sizin nasıl bir yol izleyeceğinizi belirliyor. Fakat yani bunu geçersiz kılacak bir şey değil. Bu bizim yazabileceğimiz hani verilmiş iki nokta arasında bir mesafe bu. Yani burada da siz nasıl bir yol çizerseniz çizin, yapmaya çalıştığınız şey bunu bir line integralini almak. Line integrali almak için de birbirine sonsuz derecede yakın iki noktayı alacaksınız. Uzaklığa ds diyeceksiniz. Bu ds de bu, yani başka hiçbir şey olamaz.
Anladım, tamam.
Yani kartezyen koordinatlarda birbirine komşu iki noktanın arasındaki mesafe bununla veriliyor. Tamam, Öklidyen kuan karşılık geliyor falan ama şey değil. Nasıl diyeyim? Öklidyen olmasına gerek yok. Çünkü bu zaten hani şey yaptığınız zaman, infinitesimal uzaklığa baktığınız zaman bütün uzaylar zaten flat olmak zorunda. Yani Öklidyen olmasa bile uzayınız sonuç böyle olacak. Dolayısıyla sizin hızınızın hani ne bileyim relativitede bir şeyler falan değişecek olsa bile bu infinitesimal uzaklığa birbirine komşu iki nokta arasındaki uzaklığa bir etkisi olmaması lazım. Çünkü o kadar zoom ettiğiniz zaman, birbirine komşu iki noktaya geldiğiniz zaman bütün uzaylarınız zaten düz olacak. Eğer fiziksel bir uzaysa.
Tamam hocam, anlıyorum. Yani relativistik bir şey düşünmemiştim zaten ama demek istediğinizi anladım.
Peki.
Teşekkür ederim. Yok yani anladım. Ben sanırım bir notasyonla ilgili kafam karıştığı bir nokta oldu. O yüzden hani
Ya o çok normal. O yüzden ısrarla söylüyorum, kendinizi de yapmanız lazım. Hani böyle baktığınız zaman bir şeyler, ha evet ya oradan geldi, buradan geldi falan filan, ama onu nasıl kullanacağınızı kendiniz görmeniz lazım. Yani kafanızın karışması aslında hani dalga geçmemek gerçekten iyi bir şey. Biraz kafanızın karışması lazım ki sorun nerede olduğunu anlayıp sorunun üstüne gidebilin. Hani kafanız karışmıyorsa ileride karıştığı zaman çözmeniz daha zor. Şimdi karışması bir parça aslında daha iyi bence. Keşke herkesin kafası biraz karışsa. Böyle söyleyeyim. Benim de kafam karışıyor zaten. Ben bu iş sonuçta tamam bu benim çalıştığım bir konu ama hani başka bir şey yapıyor olsam bir sene bakmasam ben de unuturum bunu yani. Şey değil. Mantıklı bir şey değil. Sezgilerinizle çıkartabileceğiniz bir şey değil. Notasyon çünkü. Notasyon öyle bir şey.
Anlıyorum hocam. Teşekkür ederim. Sağ olun.
Ya belki şöyle bir şey aklıma geldi. Şimdi biz dt eşittir ds bölü v dedik ya.
Yes.
Hani orada v de aslında değişiyor. Belki ondan dolayı öyle bir şey düşünmüş olabilir arkadaş. Hani v'nin değişimini oraya katmamız gerekiyor gibi mi? Şimdi benim aklıma geldi de öyle deyince.
Ona söyleyebilecek bir şeyim yok. Hani yani bunlar birbirinden bağımsız şeyler. Birinin değişmesi öbürünün niye değiştirsin ki? Bu birbirine
Evet, v
konuşma
zaten
noktasındaki
değişiyor.
uzaklık. Bu sizinle hızlı hareket ettiğimiz. Bu nasıl bunu etkileyecek ki?
Hı hı. Tamam.
Hani dediğim gibi kafalar karışabilir. Karışması da lazım biraz ama hani o kafa karışıklığı nasıl çözerim bilmiyorum. Bunların sadece bağımsız olduğunu görmeniz lazım. Eğer karışıklık oradan kaynaklanıyorsa. Başka ne söyleyebilirim bilmiyorum açıkçası. Bir şey de tabii hani bu çok genel bir strateji zaten. Hani graduate school'da herkesin yapması gereken bir şey. Birileriyle beraber çalışmak. Yani böyle karışıklıklar olduğu zaman yani benim açıklayamayacağım şimdi arkadaşlarınız açıklayabilir size. Faydası olur. Okay, where were we? We got the function and we need to get this, but there is actually something that Goldstein doesn't do as well, but we could do. Instead of this, we can take this, okay? And then where's my, so then it's going to be mgx equals a half m v squared, and this is going to become x. Okay? I can always do this. I don't need to throw x and y in a particular way. The function is still going to look like it's a function of b, y prime and x. So I can do this, but now the earlier Lagrange equation solution is going to become simpler. Right? Now I made the y coordinate cyclic, so it went away. So the derivative of this is going to we're going to take the well, just do this. X of del f by del y prime equals 0. This is why what my Euler Lagrange equation looks like. So again, if this is 0, this means this is constant, and yeah, let's just copy it from here. And if that constant is conveniently called 2a to minus a half, so 1 over the square root of 2a. The reason why you do it this way is that when you write this differential equation, when you actually take the derivative and this form, you end up with a differential equation that looks like, after squaring, plus y prime square is equal to 1 over 2a. Okay? And this is a single, well, it's a first order differential equation. It can be solved by quadrature, and the quadrature that gives this is x dx by 2ax minus x squared by half. So going from here to here, it's just algebraic manipulation. There isn't anything fancy, but as I said, whenever you see an equation like this, it can always be solved by quadrature. So that's something to keep in mind. And now, how do you solve this one? By change of variables. By actually two change of variables, trigonometric substitution plus translation, but they can be put in a single form, like so. So this is the variable change you make, and then the dx becomes this. And the equation becomes very simple. A1 minus cosine theta d theta. Okay. And then the result is a cycloid. The cycloid is the curve traced by a circle that's going around in a circle. Sorry, that's going around in a line. So yeah, something like this. So as this rotates over here, the point on that is going to trace a cycloid. So if you take a look at this in the book, it's a much better drawing. Now, so the Brake-Stockholm problem is important, and it has some, nice solutions. So there's a YouTube channel, Blue Brown. He makes mostly math videos, but he also has a video on Brake-Stockholm problem. So if you want to learn more about this, you can look at that. That there was one with him and Steven Strogatz talking about the Brake-Stockholm problem. I'm not sure if it's on Blue Brown's channel or on Strogatz's channel or somewhere else, but they made a collaboration. So if you email me, I'll find this video and post it on OptiPlus. Otherwise, you can just check YouTube for this. It's a nice video, and it starts with kind of a puzzle. So I suggest that you don't watch it entirely. Just to try to solve the puzzle yourself, and if you fail, you can of course watch and learn the solution. It's insightful either way. All right, now I'm very tired, but I'm going to go on for a little bit more because I want to generalize this and just get the actual earlier Lagrange equation. So far, the equation we've been using actually is referred as the other equation, but I'm going to make the multidimensional generalization, and then I'm going to stop because I am really tired, but I don't want to stop here. I want to just take one step further. Now, so how do we get the Hamilton from the Hamilton's principle to Lagrange equations? That's the thing. And to do that, you need to explicitly define your function inside the integral, and it is going to be not a function of just one coordinate and one dependent and one independent variable, but it's going to be a function of many dependent variables and one independent variable. Okay, so R delta J. So this is from Hamilton to Lagrange. Okay, how you get this Lagrange equation of motion for Hamilton's principle, and it's just a generalization, but it's important. So we're going to have, so going from point 1 to point 2, some function of y1 of x, of y2 of x, and and then y1 prime of x, y2 prime of x, and then x of dx. Okay. Now all of these. So remember, we said that we are going to introduce deviations by changing this function y a little bit, and now we are going to change all of these y's a little bit using the same small parameter but different arbitrary functions. So our y1 of x and alpha is going to be y1 x0, the y1 corresponding to the correct path, plus alpha eta 1 of x, where this function has the same property. It's arbitrary, differentiable, and it's vanishes at the endpoints. Okay? And then you do the same thing for the other stuff, and so on and so forth. Okay, for all the y's. Now, another property now and I are independent. And this is going to become important when we discuss the constraints and things like that. So they're independent, differentiable, and vanishes at 1 and 2. otherwise arbitrary. And these are the properties. Now you go through the same steps. You basically take the variation with respect to y, and then there's going to be chain rule. Sorry, x. There's going to be chain rule coming from y1, y2, and so on and so forth, and then y1 prime, y2 prime, and so on and so forth. And you can write this integral then as some sum. Okay. So this I is over all those values of y, and it's going to be del f by del yi minus p by dx. It's essentially the same steps. You're just applying the chain rule. Dx. Okay. So again, integrate by parts. So you keep the first part, you integrate by parts the second part, and so on and so forth, and you end up with this situation. Now, for this delta yi, what I mean is the variation of del yi by del alpha at alpha equals 0, and then the alpha. Okay. Now we said that the Hamilton's principle and Lagrange equations are equivalent, so derivable from each other when the constraints are holonomic. Okay? So for the holonomic constraints, our yi are going to be independent, and when yi are independent, so are this delta yi. So let's write this down. So when yi are independent, which is our case, because our constraints are holonomic, and this can always be written in terms of generalized coordinates and so on and so forth, this delta yi are also independent. Okay. Now, you apply this trick twice. Okay, so we want to say that this is going to be 0 all the time. So I want to be able to just take this and write this as 0. Now the first thing to do, that we take this out. Okay, we take the sum out and look at the integral. Now for that integral to vanish, then these terms inside, for that sum to vanish, each term in the sum has to vanish. Okay, so I first move this out of the integral, and I'm going to adopt the sum of integrals. And for that sum of integrals to vanish, each integral has to vanish. Do I need to write this down? I really don't want to write this down. Someone wrote something. This one, I guess. Oh, maybe. But let me repeat this. So we switch the order of the sum and integration. And then that sum is going to be 0. This variation is going to be 0. But for that sum to be 0, each integral in that sum has to be 0. Okay. Yeah, as I said, I really don't want to write this down. But then, if each integral in that sum is 0, so I'm written this way, then for each of those integrals, I'm taking this function and multiplying it by some arbitrary function, arbitrary independent functions. Okay. Which means that these functions has to vanish identically. There is no other way that I can make these vanish all the time. Okay. So then you end up with delta f, delta yi, by dx, delta f, delta I prime is equal to 0. So this is just taking the basic idea of writing the Euler equation for calculus of variations and generalizing it to multi-dimensions. So this is correct for every I. Okay. Now we did use the fact that these are independent, and that requires that the constraints are holonomic. And yeah. Now to go from this to Lagrange equations, what you do is you take your x into time, take your y or yi into qi, and take your f into L. And that's it. You get this one turns into Lagrange equation of motion. And we're going to utilize this. Now, before solving some examples, I'm going to look at the case where we introduce the constraints. So we are going to have three kinds of constraints. Holonomic constraints. So generally, you deal with holonomic constraints by introducing some generalized coordinates that are completely independent of each other. Then everything is very simple. Sometimes it's not possible. Sometimes it's not possible or convenient, or just didn't see the trick. There is another way to handle the holonomic constraints, and that in fact leads to the constraint force as well. Okay? So, for example, for the Atwood's machine, when you solve it with the generalized coordinate, just the distance of one of them from the ceiling, something like that, then you don't get the tension, the constraint force in the rope. But if you actually write two generalized coordinates, the distance of both of them from the top, and then write the constraint, which is holonomic, then that allows you to calculate the force as well. Generally, you don't need this, but it's one way to calculate it. The second kind of constraint we are going to look at is semi-holonomic constraints. So we are not going to have just a function of coordinates being equal to 0, but a function of coordinates and coordinate derivatives being equal to 0. And then there are other kinds of non-holonomic constraints which we are not going to look at. Yeah? Because if you're going to deal with those, then you don't use variational principle. It's just it's something else. Every case is different. You handle them differently. And if we come to an interesting problem like that, I'm happy to go over those techniques. But doing it in the abstract is completely useless. And the book actually admits this. So it's not, well, maybe not this edition. This edition is different. I'm more familiar with the second edition of the book. But the second edition definitely says, okay, we are showing you this, but you're not going to use it. And I agree, you're not going to use it. But we're going to look at this, and at least we're going to know how to calculate the semi-holonomic constraint situation and how to calculate the constraint force. And that, incidentally, the equation that allows us to calculate the force is known as the Lagrange equation of the first kind, which was referred in the question I showed at the beginning of the previous lecture.